All right, so we've gone through all kinds of different factoring, where you're factoring the greatest common factor, you're factoring x squared plus bx plus c, ax squared plus bx plus c. You've got a difference of two squares. We really talked about all kinds of different things, right? Wrong. Really, all we've talked about is factoring two different kinds of polynomials, where we take ax squared plus bx plus c, and when you factor that, you're going to get two parentheses, where first times first is equal to the first, last times last is equal to the last, and then manipulate these numbers so that you get the bx in the middle. Or the other thing we did was a difference of squares, a squared minus b squared, where you start with a perfect square, you end with a perfect square, and it has to be a minus sign. And when you factor that, you get two parentheses, and it's a plus b and a minus b. And really, that's all we have done this entire chapter, is just those two things. Kind of hard to believe, right? Because we've taken a look at so many different variations of that it's kind of hard to fathom that's all we've done, is just factoring two things: a trinomial and a binomial of two perfect squares. So let's put it all together here, right? Number one, first thing when you factor any polynomial is you look for a greatest common factor. And when you do that, you're going to get one of three things. When you factor the GCF, you're going to have the GCF times an ax squared plus bx plus c, and then that will get broken down into two binomials. Number two, when you do a GCF, you could end up with the GCF times a difference of two squares, which would be the GCF, and then two sets of parentheses, two binomials. Or the third thing that you could end up with is if there is a GCF, that you'll end up with a GCF and something in the parentheses that will be prime. You're going to have one of these three things. Oh, actually one of five things. You're going to be factoring ax squared plus bx plus c, a difference of two squares, a GCF, and then have ax squared plus bx plus c, a GCF, and then a squared minus b squared, or you're just going to have the GCF, and whatever's left over, that's going to end up being your answer. When it all boils down to it, that's all we're doing this entire chapter. Now, granted, after I look for the GCF, the little trick that I learned a long time ago is after you look for a GCF, look for any perfect squares. That's going to help out big time, is if you can identify perfect squares right away, and here's the reason why. Number one, always ask yourself, is there a greatest common factor, x squared minus 16x and positive 64? Do we have a GCF here? No, we do not. So what form is this in? Is this ax squared plus bx plus c, or is this a squared minus b squared, a difference of two squares? Well, it looks like it's probably in the form of ax squared plus bx plus c. So let's take a look and see if that can be factored down into two other binomials. Well, to get x squared, we have to have x times x. And look at this, 64. Perfect square. Square root. I'm going to try 8 and 8. I have to come up with negative 16x. The only way to get positive 64 is if the two signs are the same. This says they both have to be a minus, and by golly, there we go, x minus 8, x minus 8. Number two, is there a GCF? No, there's not. So which form is this in? Is this ax squared plus bx plus c, or is this a difference of two squares, or is it prime? Because that's the only really that comes down to the only options. It's either going to be prime, ax squared plus bx plus c, or a difference of two squares. Well, we know it's not a difference of two squares because we have three terms here. So this is in the form of ax squared plus bx plus c. Remember, a is equal to 1 here, so that's not going to be a big deal. It's going to be broken up into two parentheses. We only know that x times x is x squared. Look at this, 121. Isn't that a perfect square? The first thing I'm thinking, class, because that thing's jumping off the page at me saying, here I am, I'm a perfect square, take the square root of me, and put in a couple of plus signs, and you've factored this one as well. Number 3, I don't like the way this one's written, so I'm going to rewrite this so that we have descending powers, x squared plus 18x plus 81. And look at that. We have another ax squared plus bx plus c. I'm going to start with x and x. I have to have plus and plus. Square root of 81, 9 and 9. Look at that. I get 9x and 9x and my 18x in the middle. Same thing with number 4. These are called perfect square trinomials. They're perfect squares and they are trinomials. They're perfect squares because when you factor them, you get the same root both times. So x plus 5 times x plus 5 makes that a perfect square trinomial. Number 5. All right, now 16, 24, and 9. I know I'm supposed to look for a GCF, but I'm seeing 16 and 9. Yeah, we don't have a greatest common factor here. So I'm going to have to break this up. This is an ax squared plus bx plus c, but look at what we have here. 16n squared. That should be jumping off the page at you and saying, hey, take the square root of me, and I get 4n. So I'm going to be starting with 4n and 4n. And look at this. It ends in 9. So how about 3 and 3? The two signs have to be the same. They both have to be minus signs. Do I get negative 24n in the middle? Here's negative 12n, and another negative 12n is a negative 24n in the middle. Another perfect square trinomial. Look at number 6. Well, again, I'm looking for GCF here. We don't have any GCF. We got 4 and 9, though. Those are perfect squares. Got another perfect square trinomial. To take the square root of 4m squared, it would be, whoops, I don't want 4 there, right? I want 2m times 2m. The square root of 9, 3 times 3. Give me a couple of plus signs in there, and that one's factored. All right, so here's where we really start putting it all together, number 7. What do you always look for first? Well, if you said anything other than a GCF, we need to rethink what you're talking about, what you're trying to do here. You always, always, always look for a GCF first. I have one in this case. It's an X. And what's it going to look like? Now, it's either going to end up looking like this, or end up looking like this, or end up looking like this. If I take a GCF out, I'm going to have X times the quantity. Now, since there's 3 terms here, I'm going to have 3 terms in my parentheses. Now, x to the third over x is x squared, plus x squared over x is x. And the last term, the x's cancel, minus 2. Now, we have to look at what's inside the parentheses, because I'm either going to have an ax squared plus bx plus c. I'm going to have a difference of 2 squares, or it's going to be prime, and I can't go any further. What do we have here? Well, it looks to me like it's going to be ax squared plus bx plus c. So let's see. Now, I'm not saying that we can, but we need to look to see if we can factor that again. So now always bring down the GCF. It stays out there. And if this can be factored, it's going to be 2 sets of parentheses, where we would have to start with x times x. The 2 signs would have to be different, plus and minus. I can only use 2 and 1, right? And I need the bigger number, the 2 to be a positive and the 1 would be a negative, and that turns out to be x squared plus x minus 2. So it was an ax squared plus bx plus c. I could factor it again. Final answer, x times the quantity, x plus 2, x minus 1. Look at number 8. It's looking like it's going to be a difference of 2 squares, but 2 is not a perfect square and 18 is not a perfect square. So what do I do? Oh yeah, always look for what first? A GCF. And what is it in this case? We've got a 2 in common. So what happens when you factor that out? We'll have 2, look at how this is going to be written here. We have the GCF outside and then x squared minus 9 on the inside. Now, as far as I can tell, that's a difference minus sign of 2 perfect squares. X squared is a perfect square. Remember, it's got an even exponent. You know, 9's a perfect square. See, this thing can be broken up into 2 more parentheses, right? X times x is x squared. 3 times 3 is 9. 1's plus and 1's minus for a difference of 2 squares. Remember that? We got to have a plus and a minus here. Bring down the 2, and here is your final answer. Always look for a GCF first. In number 9, you have a 3 that's in common. Is that all? No, because you also have a y in common. So the 3y gets written down. It gets divided out, and it looks like we're going to have something like number 2 over here. What's 3y divided by 3y? Any number divided by itself is 1. Bring down your minus sign. 18 divided by 3 is 6, and x squared. So you have 3y times the quantity 1 minus 6x squared. Now, 1 minus 6x squared, that looks like it should be a difference of squares, right? Wrong again. Why? Because 6 is not a perfect square. So where that leaves us is right here. 1 minus 6x squared cannot be factored any further. So this would be our final answer, 3y times the quantity 1 minus 6x squared. Number 10. I know it's already a difference of 2, exactly the way it's written, it's already a difference of 2 squares. But remember, when we say factor completely, it means to factor completely by taking out the greatest common factor. Other than 4, do we have anything else in common here? No, we do not. So we take out the 4, and we get x squared minus 25y squared. Well, can the x squared minus 25y squared be factored again? Well, isn't it a difference minus sign of 2 perfect squares? X squared is a perfect square because of the even exponent. 25y squared is a perfect square because 25 is and y squared is. So this gets broken down into 2 more sets of parentheses. That's supposed to be a 5 there. Bring down your 4. So we're going to have the square root of x squared is x. It goes here and here. The square root of 25y squared is 5y. Goes here and here. 1's plus, 1's minus, and now you're done. Number 11. All right, 6x squared plus 15x minus 9. Let's see now. How am I going to break up the 6x squared? Oh, that's right. I'm not. Why? Because there's a 3 in common. Always, always, always. So what is that going to leave us? When we factor out that 3, we're probably going to be here. Ax squared plus bx plus c. Let's see if we're not. So I'm going to have the 3. And then it's going to be times the parentheses. Now that'll be 2x squared. And then 50 divided by 3, that'd be plus 5x and then minus 3. Now that looks like it should be factorable. Let's take a look, and we've got to do a final thing just to make sure. Let's see now. We're going to have 3, and then if this can be factored, it's going to be 2 parentheses. And if it can be factored, the only way to break up the 2x squared would be 2x times x. Got to have 2 different signs, and I need to end up with positive 5x. Now remember though, I can only use factors of 1 and 3. So it's either going to be 1 and 3 like this, or 3 and 1. I'm going to try 1 and 3 first. And the reason why is because I need to end up with 5. And I'm going to mark on and through number 13, don't do this. But here I'm going to get 6x. And here I'm going to get 1x. And because I need different signs, I need a positive 6 and a negative 1. That'll give me my positive 5. So I'm going to go with plus 3 and minus 1. And that one did get factored again. So I end up with 3 times the quantity, 2x minus 1x plus 3. But we have to take that 3 out first. Number 12. Let's see now, 36, 45, and 9. It looks like I might have a 9 in common. And then we have a to the second, a, and a. That's an a that's in common. Then I have b to the third, b to the fourth, and b to the third. I have a b to the third in common. So I have 9a b to the third times the parentheses. 36 divided by 9, let's do this in a different color. 36 divided by, that'll be 4. A squared over a is a. B to the thirds cancel out, minus. 45 divided by 9 is 5. A's cancel B, plus 9's cancel, A's cancel, B to the thirds cancel. So just close the parentheses like this? No, we need a 1 here. Now I need to decide what's inside the parentheses. If what's inside the parentheses is ax squared plus bx plus c, I'll factor it again. If it's a difference of 2 squares, I'll factor again. But if what's inside the parentheses is prime, this will be my final answer. 4a minus 5b plus 1. The only thing it could be is an ax, because there are 3 terms, the only thing it could be is ax squared plus bx plus c. And do I have that? Do I have an a squared? No, this is done. We're done after factoring the GCF. There's your final answer. Number 13, 16, 40, and 25 does not look like a GCF. Oh, this one's going to be trouble, isn't it? Look at all these huge numbers. Not. Look, 16a squared. What did we say earlier? Look for perfect squares. And if you have a perfect square, the first thing I'm going to do is I'm going to try the square roots. So 4a times 4a would get me 16a squared. And look at this, 25b squared. Ha! Another perfect square. 5b times 5b would get you 25b squared. They both have to be the same sign because it ends in positive 25b squared. This says they both have to be minuses. Does that give you negative 40ab in the middle? Well, here's negative 20ab. Here's another negative 20ab, and there's your negative 40ab in the middle. Good job. 4a minus 5b, 4a minus 5b. Last but not least, let's take a look at number 14. Let's see now. We have an x squared, it looks like, and it looks like that's about it. So I'm going to have x squared times the quantity. All right, those guys cancel, so y squared plus, now we have a y there, and x to the third over x squared is x, and minus 1. Is this in the form of ax squared plus bx plus c? No, it's not, because we have x's and y's all mixed in here together. This is your final answer. So there it is. That's how you put it all together. You're going to be looking for If it's just simply ax squared plus bx plus c, break it up into two parentheses, right? Just like we did here. And if it's a difference of two squares, break it up into two parentheses. But if there's a GCF, we'll have the GCF, and then you have to look at what's inside the parentheses to see if it can be broken up again, because it's ax squared plus bx plus c, or is there a difference of two squares inside, which means you're going to just do square roots and one's plus and one's minus, or can that thing be factored at all, that last polynomial? If not, you're just going to have GCF times the polynomial like we did in number 14 there. So anyway, there it is. That's how you put it all together. And well, good luck on your test. Remember, you can always view the practice test that's coming up. Good luck. We'll see you guys in class.